Now we go through the different components and look at what are the properties that are required for the components, and I will show you also some picture of them. So this part of the lesson will be easier. Someone left. There is someone outside. Still someone outside? No. Okay. Okay, first of all, catalyst layer. We start from this one because I told you that most of the technology is there. So today, most of the research centers are working on this. So the core of the technology is in the catalyst layer. So what we want to have is a high ECSA. So we want to have that for every single square centimeter of our fuel cell, we want to have hundreds of centimeters of platinum available. Okay? Because it's on the surface that the reaction happens. So what is important is not the mass of platinum, but what is important is the surface. It's the surface of platinum where the reaction really occurs. So we want to have a high CSA with low loading of the material, low mass. So what we want to have is, you see here, a good ratio S, the surface, divided the volume. The surface is proportional to squared R or squared D of our nanoparticle. Okay? Okay, this is the diameter. The surface is proportional to square of the diameter. The volume is proportional to the cube of the diameter. So this ratio is proportional to 1 over D. So the smaller the nanoparticle, the higher is the surface compared to the volume. Okay? So generally the nanoparticles are about 2-5 nanometers. This is the order of magnitude. You will see that going to very low diameters, some degradation mechanism will be enhanced. So the lifetime will be reduced. But in principle, what we want to have is very small nanometers. In the last, say, 10 years, significant progress in the production of this kind of material is being made. So there was an important change in the performance and also cost of these components. Then another thing we want to have is a good utilization of platinum. So we want to use it all as much as possible. So we need to optimize the contact between platinum, ionomer, and void inside our catalyst layer. We want to optimize the structure and the contact. Okay? Then we want to have a very good electron conductivity, the carbon phase, and very good H+ conductivity in the ionomer phase. Finally, we need to have a pore size sufficiently high, generally higher than some tens of nanometers, in order to have a good gas transport. If you don't have good gas transport, you have an important gradient in the activity, also in the catalyst layer. Okay? So we need to control the porosity. And finally, we need to keep an eye on the durability. This is a crucial point. So we have to optimize the material, not only at the beginning of life, but for the whole life. So we need to have all these things together. And then imagine that all these things, all these material are working up and down in a very dynamic cycles. So all these must be optimized in order to work in different operating conditions. Let's take a picture. This is a picture with the microscope. This is a SEM, scanning electron microscope. These are 20 micrometers. So you see, this is a quite old membrane. So the membrane here is 50. This is for stationary application. It is quite thick. This is the anode. I would say about 10 micrometers, and this is the cathode, about 20 micrometers. For automotive application, all these dimensions are smaller, because this is made for high durability. The one for automotive are thinner and are for high performance and short durability, lower durability. Okay. Then if you zoom, okay, this is the cathode. So we just zoom this part over here. Okay. And you see that the porosity, this is still SEM in age. You see the porosity. So these are the black, I told you, carbon spheres. And the carbon spheres are in the order of 50, 70 nanometers. So this is the order of magnitude for the spheres. Very small. They are porous, and they're like this. And then this is an image with a TEM, transmission electron microscopy, that can go to very high resolution. And these are 200 nanometers. And all you can see, this shroud of white dots are nanoparticles. Then you can see also some big one, but this is a defect. These are defects. So these are nanoparticles. It's a shroud, a cloud. It's a cloud of nanoparticles. And if you zoom even further, let's jump 1 second. Here they are. So these are really nanoparticles. And microscopes and technology can tell you today how big they are. Okay? And you see there is a certain range. There are very small ones. Okay? Here they are very small in this area. And over here they are larger. And these ones that have been underlined are bigger ones. So in this study we identify some bigger one that we didn't want to have. So there are technology to go there till this kind of dimension. Now what I would like to stress here is the composition. Look, this is the shroud of nanoparticles. No, sorry, this is what you look at with the microscope. Then you can make a mapping of the composition. And the red dots are nanoparticles. The blue, light blue, is the carbon. So you see there is a quite good distribution. There is a quite good distribution. And then here with purple, you have the ionomer. So if you imagine to superimpose them, you see there is that the study here was to make it more uniform as possible. And even if you try to make it uniform, of course you can't reach all the particles. So today, the number of particles, the share of particles that are being used increased very much, but it's still not 100%. Okay? And now we make a calculation. Here I would like just to show you what is the shape of the distribution. This is the particle diameter, and this is the distribution. It's not a perfect narrow distribution. Of course, when you produce this material, you have a control, but it's not a perfect control of your material. Here you see the maximum is about 1.5 nanometers.
Professor?
Yeah.
What kind of technology is used to deposit these?
To deposit.
Yeah.
Generally, it's a spraying. So you buy a carbon that already supports the nanoparticle, and this is produced by. Generally, there are pyrolytic ways. There are different ways, but then you can directly buy a cluster of carbon with the particles. Then you make a ink you have some solvent, you put some ionomer, you make a ink, and you can do spraying or deposition like with blades. But blades today is not used anymore. Generally, it's spraying technique. There are also roll-to-roll techniques in which you have this membrane, large membrane moving. There are already automated processes in which they spray over it onto the membrane directly. And then there is, of course, a process to let the solvent evaporate. That's the technique. The point is how to produce the ink. Most of the work in producing a good ink with a good dispersion, they call it, and then to apply them. But let's go on. Now, when you make the calculation here, I put a simple calculation. So we can say over here the diameter. We consider two diameters. So it's the volume to area average diameter. We had these are real cases. One case with a diameter 2, average 2, and one case with average 5.5. The real area of these spheres should give 140 square meter per gram of platinum we are using. Okay? So, and consider that generally in 1 square centimeter you put 0.25, 0.4 milligrams of platinum. So we know the amount per each square centimeter. Now, you should get 140 square meter. In reality, there are ways to measure it, to measure the real active area, not the one made. This is made from calculation. Okay? This is 100% utilization of platinum. In the reality, we get 70 or 80. It means that we have a utilization of platinum of 50-60%. Okay? If you make a little larger, there is better control. So the theoretical is 50. You get 30-35, so you have a 60-70% utilization. It means that in the best case, you are not using 1/3 of platinum. So it means that till 10 years ago, it was like 20%. This number were about 20%. So there was a big increase, but there is still room. This is what the message here. There is room for improvement on the utilization of platinum. Okay? And that was the catalyst layer. Then, looking at the membrane, what we want to have in the membrane is a high proton conductivity. And here, what we have to consider is the water content. You will see that water content is crucial to give high proton conductivity. Then we want to have a minimal electron conductivity. Because remember that we assume that is a perfect insulator. Okay? We assume it. But polymers are never perfect insulators. There is always a very tiny current that can pass through, depending on the delta V that is applied. Then we want to have a very low gas permeability. That's another thing. We assume there's a perfect impermeable membrane, but this is not perfect. So we have to really pay attention to that. And finally, of course, good mechanical and chemical stability. But let's look into these three things. So first of all, how membrane works. So you have a backbone. Generally, this is the most used membrane. They are based on these mechanisms. There are different producers. For example, DuPont, Solvay, Gore, 3M, all the big guys of the polymer produce their own polymer. Okay? It's a very difficult process to produce this, and just few of them are really stable in time. But anyway, you have a sort of backbone like PTFE, Teflon, okay? And on this backbone, there are some SO SO3H, let's call it SO3H group. Okay? Now, if you put water inside, what happens is that water is detaching this H plus that is over here. So if you put enough water, you let this H plus get out from this group. And so the group becomes SO3 minus. Okay, look at here. If you have water inside, this H plus will get out. So if you have a well-hydrated polymer, all the groups, or most of these radical groups, they are in the ionized form. They are like this. And our H plus is becomes hydronium, so you have water all around. So the H plus will have 2 or 3 molecules of water around, and it will be like this. Okay? This is our H plus. So H plus is not like a proton. It's a proton with around water, because I remind you that water is bipolar. Okay? So it will be attracted. So if you have water, we have a high concentration of H plus in our membrane. And these groups are able to move. Okay? Back and forth. But we need water. If there is not enough water, not enough H plus. Then there is also another effect. Water will fill. You have more water around, water will fill the pores. So the pores are large, they are open. And so the interaction of these with the boundary, the walls, is less. So there are 2 effects. One is chemical, so detaching H plus. The other one is keeping the pores wide and open. At the end, we need to have high water content in order to have a good conductivity. Look at here. If you put a membrane in a certain condition, controlling the relative humidity of water in the environment around, and then you measure the conductivity, here is the conductivity, you see that you have a moving from 20% to 100% RH, relative humidity, you change, look, 2 order of magnitudes, almost 2 order of magnitudes the conductivity of the polymer. And of course we want to work over here. So we need to pay attention not to go to very low value of relative humidity. Okay? So if we don't have enough water, our membrane will not conduct H+. That's the point. You are not damaging it, but it doesn't work. It doesn't work. Then, I remind you that our losses are like this. This is the thickness. So we want to reduce the thickness. In fact, now the standard thickness is 25 microns. Till a few years ago it was 50, now it's 25. In our lab we are testing now thickness about 10. So there is considerable improvement also on this, and now they are able to reach these values because inside the membrane they are introducing a reinforce. So there is a sort of a net, not like Gore-Tex things, so it's a net that is very strong from the mechanical point of view, and then they applied some conductive ionomer on it. So it's like it's a net like this, and then they introduce some ionomer all around. But the mechanical part, very bad, I know. But the mechanical part is given by the reinforce, not the membrane itself. Then, of course, the other thing, we want to increase the conductivity. That's so. Yes, that's so. But now let's look at what's happening in a fuel cell about the membrane. There are two things that might happen regarding the membrane, and they happen. They happen always. So the membrane is not a perfect insulator, it is not perfectly impermeable. So, first of all, let's consider the gas crossover. Hydrogen can cross over, so can go through the membrane. So a little of hydrogen will go through. So there is an undesired H2 flow from anode to cathode. Why hydrogen? Because hydrogen is a very small particle, molecule. So it will dissolve in water and move easily in the pores because it's small. It's not directly in a gas phase. It will dissolve in water. And what's happened? Then we have hydrogen arriving at the cathode. So imagine now that we have no current here. It's open circuit. But we have hydrogen and air flowing. So no current. Delta V is the equilibrium one. Okay? But some hydrogen is going through. When hydrogen will arrive at the cathode side, what's happening?
What?
It reacts. It reacts. But not chemically. Electrochemical. Because we have a very high potential and you have hydrogen HOR happening over here. So hydrogen will split in H plus and electrons. Then over here you have oxygen coming that will give you our ORR. I don't write the reaction, you know that. And in between there is, of course, electron current and proton current, all inside the catalyst layer. Everything is happening inside the cathode catalyst layer. So you don't use that current. Okay? So imagine, I look some face, I'm not convinced. Let's go back. And this is a particle of platinum. This is another particle of platinum. Okay? Now we have hydrogen. Hydrogen is arriving to this particle. And then you have HOR. Okay? Then oxygen is arriving over here. And then you have ORR. What's happening? Electrons are moving in the carbon from one particle to the other. Because we have carbon. And then green, H plus will move in the ionomer. We have ionomer in the catalyst layer. So we have a fuel cell inside the catalyst layer. Do you agree? And we are wasting everything, just producing some heat. What's the result? That you think to be in open circuit. You are not in open circuit because you have some current there. So your reactions are not in equilibrium, they are occurring. So what's happening? You have losses related to mainly the ORR. Okay? A little of electron or proton transport, but almost nothing. Most of the losses related to ORR. So when you look at the red, you are on the red curve. And you think to be at zero. The real curve you have is the red. You think to be at zero, but you are not at zero current. You have a little current related to this hydrogen crossover. So the results you have in open circuit voltage, your delta V is different from 1.2 volt or from the ideal one, the equilibrium one. Because you have a little, this loss is due to the little current you have. So you are shifting your curve. You are shifting your horizontal axis. You imagine to be at zero, but you are not at zero. That's the point. So open circuit voltage, you measure and look at and see 1 volt. You say, why I don't have 1.2? Because I lost this 0.2 because here the curve is very stiff. You have a very high slope. And few milliamps are enough to let you lose 0.2 volt there. Okay? Did you get it? I say it again, once again. You think to be on the black curve. You think to be there. And you say, okay, I have zero current, I should be here. Yeah, but in reality, you are not there. The curve is this one. What you are measuring is zero, yeah, but you have this current instead. I just shifted it. You can shift the axis, it's the same, okay? Here I wrote, few milliamps per square centimeter are enough to lose 0.15 or 0.2 volts at open circuit voltage, open circuit. From now on, I will distinguish equilibrium potential and open circuit voltage. Because at open circuit voltage, I have this phenomenon. So the delta V I measure is not equilibrium, it's the open circuit that is affected by crossover. And to make things even more complex, there is another phenomenon that is the short circuit current through the membrane. Let's cancel. The membrane is not a perfect insulator. It's not a perfect insulator. So some electrons, you see here, can go through the membrane. I have a certain delta V. So here is the plus, here is the minus. And this delta V is applied on the membrane. So a very small current of electrons can go through. Once again, what's happening? ORR is occurring also for that current. So some H plus are going, some oxygen, hydrogen and oxygen are consumed. Because I have an internal current. Same as having the current externally, but I can't use it. I don't use it because it's internal. So it's doing the same thing. I think to be zero, but I'm not that zero. My system feels like having a certain current. And the current I have now is the sum of crossover and short circuit. So this effect I mentioned before for crossover is even enhanced by the presence of short circuit. It's the same thing. Okay? It's the same thing. I have two currents. One is given by crossover. And the current will be here, just inside the catalyst layer. The other one will go through the membrane. But at the very end, the cathode, that is the major loss for us guys, okay? The cathode will have a reaction rate in order to fulfill both current, the sum of the two. Okay? So we are consuming oxygen for converting hydrogen crossover, but also for the short circuit current. Okay? Some of you are not very convinced about that, huh? No. Guys, if I have a current outside, I will have ORR occurring, right? Now, if the current is inside, what's the difference? Nothing. Electron will arrive. Okay? So I have some losses over here because I have a current. So ORR is occurring. Okay? I have kinetic losses. The point is, this current over here, I'm not controlling it. It happens to be there. Okay? Due to short circuit. So ORR kinetics have to fulfill two things. Hydrogen crossover, okay? We require some ORR, but also our short circuit. Some electrons are coming, and so we have same thing. ORR is happening. What's not clear? It's not. The short circuit thing is not clear. Last time, I try once again. Hydrogen, we say, okay, forget about crossover now. Forget about it. Okay? Let's look just short circuit. Okay? Hydrogen will arrive. We have HOR occurring. Why? Because electron can go through. So we have H plus going through, but also electron can go through. If it were a perfect membrane, there was no electron, so no reaction. But now a certain amount of reaction we have it, because electron can go through a little. So this is happening. On the other side, ORR is happening. We are consuming what? We are consuming oxygen and electrons and protons. Standard reaction, ORR. It's clear now? Okay. So both these mechanisms will contribute to this deviation. So this guy here is different from OCV. That is the voltage we measure at open circuit. Okay? Now, I told you the membrane is getting thinner and thinner. These problems are getting more important because the thinner, higher crossover, and also the resistance of the membrane is decreasing, the electrical resistance. Okay? So you improvements on this regard are necessary.
Professor,
Please.
what about you also mentioned that the heating effects of the
Heating, yeah, but it's not so much.
But still we would require cooling, right? Because of
Yeah,
continuous process.
Yeah, we are later on. Yeah. Now, diffusion layer, please.
If we are use electrons, why would I use this silicon material if we use an electroconductive material in order to produce electrons at the side of the cathode?
Instead of the membrane. Because we don't want to have current here. We want to have a current externally.
But still ORR needs electrons. So a current must exist over.
Yeah, but if it's outside, I can use it. If it's inside, it's wasted. So the current inside is not useful. The current outside is useful. It's the one we are using. Okay.
We shouldn't use carbon in this case on the
Otherwise there is a
catalyst
loss
of the other side
because it's not perfectly permeable.
The carbon usage is not efficient.
But you can.
We can talk about later.
Because the
Don't
cost will
mind.
be high.
I didn't understand if this short circuit is only when the external circuit is open?
No, okay, no. In principle, you always have these two phenomena, but they are so small that when you have your own current, when you are drawing current really, they are less than 1%. So the effect on delta V is negligible. The effect on wasting hydrogel is negligible. But when you are at open circuit or very low current, you see that, you feel it. But I want you to know that they exist. Okay? And this study controlling the OCD value in time will give you information on these two mechanisms also. So you can make a diagnostic out of it. We'll talk about that. Let me go on, please, guys, otherwise we don't finish. Gas diffusion layer. So we are going through these components. I remind you that this must be electron conductive. So generally we use carbon also here. We need very good gas transport properties because it's made just to have a good diffusion towards the nanoparticles. Then we need to have a an additional property, high hydrophobicity. So I will explain better a little later, but what's important is to avoid that we have liquid water. We work at below 100 degrees C. So water, you know, at this pressure, we have 2-3 bars, 1 till 3 bars, can be liquid. So if we have liquid droplets of water, they can obstruct pores of the of the catalyst layer. And if you block the pores, oxygen cannot get in. So no reaction will occur in that area. So we really have to avoid to have liquid water around. So we make this layer hydrophobic in order to avoid pore obstruction caused by liquid water. So we help to keep liquid water away. Then of course good mechanical stability and good mechanical and chemical stability. Here just a couple of pictures. So gas diffusion layer, so-called GDL, okay, gas diffusion layer. Generally the thickness is about 200 microns, so it's much thicker than the membrane. In order to have this 2D, I told you, two-dimensional fusion, they are made of carbon fibers like this, on which some, you see that here, some PTFE, this hydrophobic polymer, is applied on. So liquid water cannot attach, cannot be blocked on this fiber, so it's easy to get the droplet away. Okay? Then on one side, on the side of the gas diffusion layer that is in contact with the catalyst layer, there is an additional layer that is called the microporous layer, MPL. The thickness is about 50 micron, is once again is carbon, must be electron conductive, and with polymer. But here the porosity is similar to the porosity 100 nanometer of the catalyst layer. This is similar. And this is very high hydrophobic, and this helps to keep clean this layer, clean from liquid water in contact with the catalyst layer. So, okay, it's a super hydrophobic region in order to keep the catalyst layer as dry as possible. Not only, if you look at it, it is very smooth. Okay, you can have some crack on it, but it is very smooth, and it has a surface that is very similar to the one of the catalyst layer. So when they get in touch, they have a good surface on which they get in touch. So you minimize resistance, electric resistance, and not only, you avoid that some fibers like this that are not perfectly oriented make a hole in the catalyst layer. Okay? Now these fibers are thick like 5 to 10. No, let me check. Yes, 5 to 10 microns. These fibers are big, and the hole are about 100 microns. They are very large. So if you have some of this fiber is oriented in the wrong way, they can make a hole in the catalyst layer. So generally, when you apply this, you are making the surface smooth, and you don't have any more this fiber getting out. So this microporous layer protect, when you assemble everything, the catalyst layer. Okay? You see how many things in order to keep it in the right way. Finally, flow field. We are there. We are going up with the dimension. We are into the flow field. And here the point is the fluid dynamics and mass transport. So we need to optimize reactant transport. We want to remove water That's another crucial point. And then we need to have a good electron conductivity once again, and chemical stability. So all the material must be very, very stable. Sorry, probably you don't realize that these systems, they have a very high concentration of H+. It means that the pH is close to 0. It's close to 1,
Wow.
2. It's incredibly low. Okay? So from the chemical stability, all this material must be really, really controlled. Otherwise, you can have some release of ions or impurities in the system that will ruin it. Okay? But now, before studying the fluid dynamics, we have to remind that our system is not really 1D. Our model was 1D, and we were able to reproduce the performance, but a real system are not 1D. Andrea Baricci, Wednesday, we will talk in details about how things can be complex. So he will make model more complex. But I would like just to introduce the so-called stoichiometry. So now, imagine that this is the channel. You see the channel? Okay? You see the channel? This is the inlet. Okay, we introduce air here. And this is the outlet. Okay? Now, along the channel, we are consuming oxygen. So at the inlet, you see that the activity in the channel was here. And the activity in the catalyst layer was this one. Then we go farther along the channel, and the activity in the channel decreased because we are consuming oxygen along the channel. And also here, the concentration in the catalyst layer will decrease. The activity in the catalyst layer will decrease. But now imagine, at the very end of the channel, what can happen is that the concentration or the activity is so low because we use most of the oxygen that we feed, that the concentration or the activity over here is close to 0. That can happen. So this part of the cell, close to the outlet of the cathode, cannot work. There is no enough oxygen. And remember that here we need to have a gradient. So even when you still have some oxygen in the channel, in the catalyst layer you have a very, very low activity, very, very low concentration. Okay? So the current you can obtain here is almost nothing. Because you have a limiting in the feeding of oxygen. Okay? That's the reason why we feed more air than necessary. And we call stoichiometry the excess of air we are giving. So stoichiometry 1 means that you are giving exactly the air and therefore the oxygen that is necessary for your current. If you give stoichiometry 2, you are feeding double the air that is necessary. Okay? So excess of air is necessary to have good performance. And if you look at here, Nernst law, the minimum flow, I call gamma. Gamma is the overall flow that I'm feeding in the fuel cell. Okay? The minimum flow that we need to feed is given by the Faraday's law. Okay? And then the real flow is the minimum multiplied by lambda, so-called stoichiometry. So we are giving a lambda time what is strictly necessary. Okay? Now, there is another point. Oxygen will be reduced along the channel. Now, what about water? Water will increase. Water will increase. It was a small amount, and then increasing. It's the opposite. So what can happen? And then another thing, we need to have also diffusion of water from the catalyst layer to the channel. So water concentration is like this. Okay? Oh, sorry. Let's do. It's small. Okay? It's like this. Then it's growing, and then it's growing. Okay? The flux of water is over in this direction. So what can happen is that here we have such a high concentration of water that we have condensation. So here we can have condensation. We have liquid water that will block pores. So close to the outlet, if we don't pay attention, we have part of the catalyst layer doesn't work because it's blocked by liquid water. This phenomenon is called flooding. And really, we really have to pay attention. So when you have hydrophobic media, as I told you, this will help in keeping at least part of the catalyst, part of the GDL, the gas diffusion layer, always dry. Okay? And then oxygen will go through there. This is what we're doing.
So the name of the process, can you repeat it?
Flooding.
Flooding.
Flooding. Yeah, flooding. Allagamento. Okay? So the water management is something crucial. We are close to the end, guys. Please survive. Water management is very important. Why? So first of all, we need to have water in the membrane. Otherwise, it doesn't conduct protons. Okay? Enough water into the membrane. Then we have to pay attention not to have liquid water. So it's a trade-off. What is typically done is a counterflow configuration, the one I reported here. So you feed air like this, air that is generally partially humidified. So air is not in the same condition you have in the environment, because if you operate at 80 degrees C, a cell can work at 80 degrees C, let's say. If you take air from the environment, RH, the relative humidity, will be very, very low. Okay? So you dry out the membrane. So if you feed dry air here close to the inlet, you will dry out the membrane. And so the conductivity will be pretty low. So we can do that. So we need to humidify air, and then we see how. We humidify a little, 30%, for example, RH, at 80 degrees C, or 70 degrees. Okay? Then we are consuming oxygen going down, but water activity will increase. Okay? So we risk some flooding, we already said, over here. Then, look at the hydrogen side. We feed hydrogen like this. Once again, it's not completely dry. Let's say that this is 30% RH, and this is 30% too, RH. Over here, we can be close to 100% RH at the outlet. So we have a gradient of water content in the membrane. So what we are having here is a flux of water from cathode to anode due to diffusion. Okay? So we are humidifying hydrogen using water that is produced along the cathode. Okay? Then we are going up, we are consuming hydrogen, and we are receiving water. This partially receiving water. So what's happening? That the water content here is increasing. Why is increasing? Some water is arriving, some water is going away with the so-called electroosmosis. What is electroosmosis? When the H plus moves, you remember that it has around 2 or 3 molecules of water. So it moves, bringing water, dragging water. This is electroosmotic drag. So when H plus moves, it brings water with it. So we have some flux like this, electroosmotic, but we have this back transport is this one I mentioned, okay? This one is this one, okay? So we have diffusion, that is back transport going back, and some electroosmosis forward. But anyway, we are consuming hydrogen. So even if the net flux is in that direction, we are consuming so much hydrogen that the concentration of water is increasing. So we start with 30%, generally we arrive here with 100% RH at the outlet. So we really have to pay attention once again not to have liquid water, but what's happening that here you have electroosmosis, but we have also some diffusion because the RH is low. You see that?
Yeah.
So we are moving the water inside the cell. Do you see that? So all these things is controlled with the flows. So you can control the flows, you can control the temperature of the system, and sometimes you are able to control also the humidification. All these flows of water help to keep the membrane well hydrated, first of all, and then to avoid to have a liquid water condensation on both sides. So there is an optimization of the flow field, the geometry of the flow field, and also the materials, the gas transport properties, the hydrophobicity of the GDL, to optimize all this internal recirculation of water. Okay? So it's more engineering, it mass transport stuff. I'm close to the end. So all the geometry will be optimized for this liquid water transport. And here I would like to mention one thing, that also delta P play a role. Of course, the delta P pressure loss will be a cost in terms of auxiliaries. So if we have high pressure drops at the cathode side for air, we need to increase the consumption of the compressor. So we need to pay attention at the pressure drop. Then we want to have a very good uniform distribution. So the geometry will be studied in detail. And we also can work in the geometry of the flow field to help water removal. For example, let's zoom this one. So between this point and this point, we have a certain delta P, okay? Because we have all this long way. This delta P, look, will induce an advective flow of air. This is due to delta P. Okay? If you have a delta P between the two channels, you have some air going through and like this, a part of the flow. Okay? Do you agree? And depending on the geometry, I can increase or decrease this flow. This flow will help in, first of all, providing some oxygen over here. So we don't have just diffusion. We can have some advection over here. So we can bring some fresh air over here. Not only we can remove water, we can have liquid droplets accumulating over here, for example. And we can bring away this water. So from the mechanical engineering point of view, all this water management stuff is very relevant. And you can contribute as much as improving the materials. Okay? So studying flow field, studying the fluid dynamics, and heat transfer over here is crucial. Andrea Barici will talk about the flow field the Toyota is using. There are patents, you can look at the geometries. There are some amazing stuff they can do, really. And there was an important improvement in the technology working on this stuff. About the materials, in the cars, metal plates are used. So metal flow fields are used. You stamp them, they are very cost effective. The point is that no metal can survive the environment. Even titanium sometimes suffer. And so some coating, proper coating and also secret coating are used to cover the metal in order to protect them from corrosion, okay? Because it's such a acid environment, at the cathode side we are a high potential, so corrosion is very promoted. In other applications in which higher costs are accepted, or in the labs, graphite composite are used instead of metal. Composite means that you have a polymer generally with some graphite in it. There is a high amount of graphite in order to have a good electron conductivity. But generally the cost is so high that some specific, just few specific applications allow the use of them. Finally, the stack. We are close to the end. We have many of these cells and we put them in series. One single cell gives us from 1 volt to 0.6 volt. This is another delta V that can be used for motors, electrical motors. Okay? So we need much higher voltage, we need hundreds of volts, or at least 10 in the worst case, but generally it's 100. So we put 100 of cells in series. And then we feed them in parallel. So all of them will feel the same hydrogen flow and air flow. Okay? So they, if you make a good stack, they will have very close situation, each of them. The only point is the temperature control. Because as you know, we have an efficiency here. If you have 50% efficiency, it means that the other 50% of energy is going to be lost in terms of heat. So we have a power, thermal power to be extracted. Okay? How we do that? we introduce, this is one cell, okay? This is another cell. We put in between, this one is a cooling plate, and in this cooling plate we have channels, once again, with liquid water. With liquid water going through in order to cool down the system. Okay? Generally it's water. You can use oil, silicone oils, things like that. But once again, the current is going through. What's happening? I can make a very simple sketch. So, this is one cell. Okay? This is the negative, this is the positive. Then you have another one. This is the negative, this is the positive side. Okay? When you put a stack, you don't take electron from the negative and give to the positive, and you put a resistor or whatever load you have here. You make them in series. What means that these electrons are going here, okay, and these electrons are going over here. So these electrons are going like this. So the electron produced by the anode of the cell 2 will go to the cathode of the cell 1. It's always electron. Okay, we don't distinguish, it's mine or your cell. Okay? So in this way, what we can do is to attach them like this, okay? And they are going like, they are flowing like this. Do you see that? We are attaching them. And so, in our stack, we have the current. Let's say that this is the negative. This is a negative. Then we have positive, positive, positive. This is the last one is positive. So the current is going like this. And then we have internal current going, sometimes as protons, sometimes as electrons, going inside. This is what's happening in the stack. But pay attention that sometimes we have a cooling plate. So also the cooling plate must be conductive, electron conductive, because the electrons must go through. So here we are introducing over here the cooling plate. The cooling plate must be conductive. Okay? Complex, I know, many things. Now, if you design a good stack, temperature is quite uniform. If the design is not perfect, what's happening is that the central part, higher temperature. And the outlet, generally the extreme, because they have convection, natural convection outside, generally they have lower temperature. But that of course can be improved by designing properly the system. That's all. So we arrived to some features. Just I would like to remind you. First of all, we really, from the engineering point of view, these are considerations from the engineering point of view. So one point that we really have to keep in mind, water management. Comparing, pay attention, drying and flooding. It's a trade-off. Drying the membrane, flooding, so liquid water in the catalyst layer. Two things, opposite things to avoid. Then, the other things, hydrogen purity. I mentioned purities, the problem of purge. Something else, we work at low temperature. Our catalyst is very sensitive to contaminants. So we really have to pay attention at CO, but not only. Air contaminants can be a problem, okay? If you go around with a fuel cell car between a Vespa or Ape or old vehicles, you can have problems. So air quality, not only hydrogen quality, can be a problem. So some filters must be used to keep cathode clean. Then working at low temperature gives some advantages in terms of dynamics. It's very fast. You can change very fast your operating condition. It's a very prompt system. Then finally, all the thickness of the components I mentioned, and also the fact you can make stack in a compact way, give a very high power density in terms of kilowatt per liters or kilowatt per kilo. So these systems are even more compact than combustion engine, if you consider just the energy part. Okay, then there are auxiliaries and other things that you can give big. What are the issues? And we will talk in 2 or 3 lessons about the issues. Today the biggest issues are cost and durability, and especially the two together. They are coupled. They are strictly coupled. You want to have high durability, you have higher cost. Okay? Then, and with this I'm finishing. So no, I don't talk about the equation. Don't worry. I just would like to mention one thing. We talk about this lamp model that was in steady state. You are able to introduce the two accumulation terms, if you like. So in the J, you have the accumulation term of the double layer. Pay attention, there is a typo over here. There is a plus, this is a plus. Please correct the typo. So we're talking about the cathode. Okay? And if we want, we can introduce also the accumulation term of oxygen. And here we have another typo, I apologize. So this is O2, it's not hydrogen. It was quite obvious, but better to be sure. So when you want to go to dynamic, you can just introduce two things and you have a dynamic model. Okay? For us, dynamic model will be important. Andrea Barish will talk about that Wednesday, because we can have diagnostics based on the dynamics behavior of our system. I already told you that the double layer will have a typical time about milliseconds. Okay? So the frequency very high. While mass transport accumulation terms, another time frame, it's very long compared to that one. We're talking about tens of seconds or minutes. So we can make diagnostic looking at what is the behavior of our system once we give a change in the operating condition. We look at the response. Okay? That's all. I will stop like this. I will put homework. So I will upload tomorrow, not today, this M file in MATLAB. This is a steady state model, but the steady state model will give you also the impedance that you will study on Wednesday. That's all. Cheers.